A warm welcome to my dear friends and dear students. A very good morning, good afternoon, good evening to all of you. And this is the Data Analysis and Decision Making 1 course under the NPTEL MOOC series. As you know, this is a 12-week lecture series under NPTEL MOOC or a course. And 12 weeks basically means this there would be 60 lectures, total number of hours is 30 hours, and each week we have 5 lectures, each being for half an hour. And I am Raghunandan Sengupta from the IME department, IIT Kanpur. So, this as you see on the screen, this is the 36th lecture. That means we have just completed 7 weeks, we are going to start the 8th week. Now, if you remember, we technically started the concept of multivariate statistics in and around the end of 29th class or beginning of the 30th class. So, we have already covered about 5 lectures or 1 week, and we covered the concept of what is a multivariate statistics, considering there are p or k number of random variables, and what are the actual characteristics of the population, what is the significance of the mean, what is of the population, what is the significance of the standard deviation of the population, the concept of variance covariance matrix, the concept of correlation coefficient, then the concept that when we are not able to find out these characteristics from the population, we absolutely use the sample and have the sample mean, have the sample standard deviation, the sample correlation coefficient, and the formulas thereof had been discussed. Then we went into the concept of the multinomial distribution, gave the PDF of the multinomial, but the PMF of the multinomial distribution, my apologies. And I also discussed a very simple example of using contraceptive in El Salvador. Then we went in the concept of other distributions like the multi-normal distribution, then discuss that it is a symmetric distribution, and we discussed the wizard distribution, student distribution, all in the multivariate case. And then we went into the discussion very briefly what is a copula. We will come to the copula later on. Then we discussed in the hypothesis testing case for the case of the multivariate distributions, and discuss, but that was only in the concept of multi-normal case, so not for the other distribution as case. And we discussed that how the sample mean and the sample standard deviations are important depending on whether the population mean is known or not known, how we basically reduce it by the degrees of freedom. The concept is exactly the same for the univariate case, and we will continue discussing that further on and go into copula and other different type of multivariate statistical methods. So, considering that considering on the multiple maximum likelihood estimations for the parameters related to the multi-normal distribution. So, once we should always see that the n minus 1, n means the set of observation, minus 1 because we are losing 1 degrees of freedom, that should be definitely greater than p. P is basically the number of random variables which you have. Otherwise, S, which is basically the standard deviation matrix of size p cross p, because the principal diagonal would be the variances or the standard error square when we are considering the sample, and the off the diagonal element are symmetric, they would basically be the covariances for the population if you are considering the population only, or they would basically be the covariances existing between the random variables considering the sample only. So, obviously, they would be replaced, and the concept of consistency and unbiasedness, which I have been discussing time and again, would also hold for the multivariate case. So, in case if n minus 1 is not greater than p, so then obviously singularity concept would come, and the t square cannot be calculated, hence we cannot basically proceed with the hypothesis testing for the multi-normal case. Now, remember for the normal distribution in the univariate case, I am sorry I am repeating in time and again, for the multi-normal distribution case, here is the normal distribution, and in the case of the point distribution you had different type of sample statistic, we know about that. Now, combining the normal distribution, we can find out the chi-square, the t and the f distribution, and obviously you had the initial z distribution, which is the standardized normal distribution. So, the counterparts which we have for the chi-square would be the wizard distribution we have considered, and we also saw that z and t would be utilized for the univariate case for finding out some characteristics about the mean of the population, and chi-square and f would be the distribution used to find out something to do with the standard deviation or the ratio of the standard deviation for the population. So, we will basically follow the same concept as we do for the univariate case for the multivariate normal distribution case also. So, now using the concept of sufficiency and concept of factorization, we obtain the following results. We state again without proof. So, obviously in the maximum likelihood estimate, what we did, and if you remember, we also discussed the general methods of moment. So, maximum likelihood estimation, the concept basically remains that if you pick up a set of observations which is small n in size, which are the observations, you assume that we obviously you do not have the values of parameters, which is mu and sigma for the multi-normal case, and you want to estimate that. So, we assume the realized values of x1, x2, x3, x4 considering for the univariate case, or x11, x12, x13 or and x21, x22, x23, so on and so forth till xp1, xp2, xp3. Obviously, this set of observations would be given such that we will try to maximize the likelihood function. Now, likelihood function, I am repeating it, is basically when the random variables take the realized values, we put them, plug them into the functional form of the PDF, find out what is the total probability, joint probability, and obviously we will consider they are independent. That independent means for the univariate case, they are independent of each other from reading to reading. For the multivariate case also, they are independent between each other, and they are also independent from reading to reading. So, once we find out the log likelihood, that means we convert it into a log function because monotonic increasing. Then the only things unknown are the parameters for the population. We differentiate, partially differentiate that, my apologies, partially differentiate with respect to the parameters, put them to 0, find them. Technically, in normal case, they give us closed form solution. So, it will be easy for us to find out the actual sample statistic or the sample estimate, which then we will try to prove they are unbiased and consistent, such that we can safely use them as the best proxy in case the population parameters are not known. So, using the property of sufficiency and concept of factorization, we obtain the following results, which we state again without the proof, and that would be true what I said, what was general statement would be true for the univariate case and the multivariate case. So, if x1 to xn, now x1 to xn all of them are vectors of size n cross 1. So, this x1, this x1 we have is basically so this one the first one is for the random variable, second number is for the reading. So, this basically means if it is a not vector, they basically mean this set which I have. So, actually what I have is this is a bold one x1, which is this. Then let me change the color for the second variable. This again a vector bold one. So, this is basically x21, x2n, x31, x3n, and this goes dot till the last one. Let me take a different color. This is xp or xk, whatever it you denote. So, this will be xp xp1 xpn. So, each is of size, okay, sorry my mistake, because color combination would basically help us to understand. So, this is for the first variable, second variable to the nth, pth variables. So, if x1 to xn are the observations from the multivariate normal distribution with the mean of mu bold. So, this is a vector of size p cross 1 and this is the covariance matrix. So, I just highlight it. This is the covariance matrix and this set of values what I have denoted is this. So, basically this will come here, this will come here, this will come here. So, the variance covariance matrix is again of size p cross p or k cross k, and then using the concept of sufficiency and the concept of unbiasedness consistency, the values of x bar, this is the x bar means the bold one, the vector one, would basically be the corresponding estimate from the sample for each and every population mean for x1, x2, x3 till xp, and S would basically be the standard error matrix of size p cross p, which would basically give us the best estimate for the case of the population variance covariance. So, this would be the case. Let me use the highlighter. So, the green one. So, this would be for this and this one would be for this one. If somebody is confused, let me remove the color. So, consider this. So, they are the sufficient and the best estimate for the case of the population mean and the population covariance variance. The sufficient set of statistics which we have considering the sample mean are complete when the sample is basically drawn, complete mean in all the statistical properties, if they are drawn from the total population, multivariate population of mean, mu and variance covariance of sigma. Now, consider the mth component of the y1, y2 till the set of observation which we have, and they are all IIDs. So, in this case consider the expected value of yi is equal to v. So, do not confuse, let us not confuse with the concept of the degrees of freedom. Then the covariance matrix given for y would be t, and then in the asymptotic sense the value would be equal to with a normal distribution with 0 mean and t as the variance. So, what we mean is that if the expected value of yi is given as v and then the variance is given by t, then in the long run in the asymptotic sense it will basically be a so called standard a simile to the standard normal deviate with 0 mean and t as the variance covariance value. Now, when we are considering the copula, we will consider that we will be talking of the correlation coefficient. So, now let me come to the covariance correlation coefficient concept, the covariance and the copula. Now, consider there are two distributions. Let me draw it. Let me draw it with in a fresh blank PPT slide. So, it will be easy for us. I will come to this discussion further on. So, let me remove it. Just give me few minutes or few seconds. Okay, now I can draw it. So, when we consider the correlation coefficient, and I will come to this slide later on. So, when we consider the correlation coefficient, it is like this. So, this is the diagram which will basically be discussed along with the just the previous. Consider is the normal distribution, and there is another normal distribution. It can be more than 2 also. So, I want to find out the relationship for these. So, this is basically x 2 and this is basically x 1. Now, what I need to do is consider I am trying to find out the relationship of x 1 x 2 at the extremes. So, obviously, in that case covariance between x 1 and x 2 would be sufficient such that from this, given the standard deviation of x 1, standard deviation x 2, we can find out the correlation coefficient existing between x 1 and x 2. But what happens if the distributions, and obviously in that case covariance is fine, it gives us good relationship. Now, see, if I expand the covariance, the formula is actually this. So, this is the linear relationship in terms of x 1 and x 2. But what happens if these two distributions, let me use two different colors of orange and a green one, and I am interested for the extremes values onto the left or right also. Now, remember here for the exponential distribution, the values fall exponentially both onto the left and the right. But in the extreme value distribution, the corresponding probabilities at those corresponding points which are on an equivalent scale distance on the EVD scale, on the extreme value distribution scale and the normal distributions are unequal, and the corresponding probabilities would also be unequal such that for a particular value happening in the normal distribution case and its probability, if we compare that, and the same probability when I consider for the extreme value distribution for the same type of value on the EVD scale, the probability in the EVD scale will be higher. Hence, when we try to find out the actual values of the excessive loss I am using in a very general sense, then the corresponding probabilities, even if they are little bit high, they have a catastrophic effect or a huge amount of effect on the overall relationship between x 1 and x 2. That means, per unit change in x 1 and its actual value on x 2 or vice versa in the normal case would be given basically by the correlation coefficient, which is fixed for any values of x 1 and x 2 you consider. But when we consider the extreme value or some non-symmetric values or distributions for which the ends probabilities are higher than a normal case, then the relationship is non-linear. That means, per unit change in x 1 or in x 2, the corresponding change in x 1 and x 2 are definitely not linear. Then we use the concept of correlation, which means in the case of the normal case, this covariance and this correlation coefficient are fine, but in the extreme value case, let me use extreme distribution case, correlation coefficient or covariance do not give us the right picture with respect to the relationship between x 1 and x 2. This I will keep repeating it when we come to the copula, but this is just a very brief background which I wanted to mention when you are basically going to study the concept of copula in the multivariate case. Obviously, considering the whole number of sets of topics we have to consider, it may not be possible of us to discuss everything, but I thought I will just give you a small brief background about that. Okay, let me go back to the initial slide. So, when we talk about correlation coefficient between x and y, we generally prefer to use one of the followings, which are the Pearson product moment correlation coefficient, the intra-class correlation factor, the rank correlation depending on what ranks they are and how you basically find out the relationship, the Spearman's rank correlation coefficient, the Kendall's tau, and the Goodman's fit or the Kruskal gamma, which are basically used to find out the relationship between two random variables, and we consider them to be linear dependent structure. But as I said, with repetition I am again saying that for extreme values this linear structure at the extreme does not happen. That means, per unit change of x1 or x2 would have non-linear effect on x1 and on x2 and x1. That means, x1 changing 1 unit would have a non-linear effect on x2, and similarly 1 unit changing in x2 would have a non-linear effect on x1. So, this is not there in the case when you consider the correlation coefficient or the different type of very simple linear correlation coefficient concept. In order to overcome that, we use the basically the copula concept, which copula concept is basically, if you remember I mentioned, is a sort of mapping which is happening between the marginals and the joint distributions in order to give us a good picture that the relationship between x1 and x2, or if there are more than x1 and x2, it may be x3, x4, these variables are there, and we are basically trying to understand the relationship at the extremes. So, this blank slides I will try to utilize that as it is. So, again continuing, but in general most random variables are not jointly elliptically distributed as normal distribution is a case, because normal distribution is class of elliptical distribution, and using linear correlation as a measure of dependent structure in such situations might prove very misleading, because it would not give us the actual interrelationship between two random variables which are not elliptical. So, hence we use copula. As an example to illustrate how linear correlation is misused, let us consider as follows. Let us consider x is normally distributed with 0 mean and sigma square as standard deviation or variance, and let us find out a random variable y which is the square of x which such that y is equal to x square. Then is expected that both an x and x y and x and y should be correlated, but if we try to actually find out the covariance between x and y, it will come out to be 0, which means that the actual information which you are trying to get using the covariances or the correlation coefficient would mean that we are not able to portray the relationship between x and y. In this case, y is basically x square, such that it does not give us what is the relationship happening between the two random variables, even though they are related. And so, in order to overcome that, we basically use the copula function. When we use a copula function, we are in a way trying to basically map from the CDF of the actual distribution which is x into the univariate case, such that there is a one-to-one correspondence. Now, this I will again explain. So, I will come to the second bullet point, which is to illustrate for the case when you have p is equal to two random variables. Obviously, it can be increased for the third case also for 3 dimension. So, what we are doing is like this. Now, background which I have did discuss, but I will again consider it again. Now, consider there are two random variables x and y, and f of x is the PDF. This would be true for the univariate case also, for the discrete case also, and this is the PDF of y. So, obviously, all the properties would hold, in the sense that if you consider capital F of x, which is the CDF, capital F of y, then obviously it would mean sum of f of x is equal to 1, the values of capital F this is small f, let me clarify this. So, sum is 1, sum is less, or the value of PDF of f of y, small f of y is between 0 and 1, and f of x, the actual value, starting basically for x tending to positive infinity, f of y, y tending to positive infinity, considering the maximum value, this is 1. Obviously, this would be true, always remember that. Now, if this is true, we will try to basically bring a one-to-one correspondence here. What we do is like this. Let me draw the PDF of x. So, consider the PDF and consider for whatever this is for y. So, this is x, this is y. Now, consider the CDF function. So, obviously, CDF function would be between 0 and 1. So, the CDF value would be this, some CDF value is this, which means that in case if you are doing a one-to-one correspondence between them, then at a certain value of x1, the f of x1 which we have, capital F of x1, would have a corresponding value of y1 such that this would always be true. In case if that is true, obviously, then then the value of x1 and x2 would be such that if I add up all the probabilities of x's till the x1 value, add them up, and add up all the probabilities for y till y1 and add them up, both of the values are equal, such that the total probability covered till that point of x1 and total probability covered till the y1 are equivalent. So, if you are able to use in place of y a univariate distribution case or a very simple distribution which we know, then doing a one-to-one mapping would basically solve our problem. That is what the main crux of the problem, or what the essence of how we are going to tackle the copular theory would be. I will discuss that in more details in the 37th class. With this, I will end the lecture, and I know that it is a little bit more theoretical than the univariate case, but I will request all the students to please bear with me as I slowly cover the theories and also cover some of the simple concept from the multivariate case. Thank you very much and have a nice day.